this video, we are going to look at Dijkstra's algorithm for the shortest path. I'm just going to take you through the basic explanation about this algorithm, give you a few steps of how you can use this algorithm, and then take you through a couple of examples, and then just wrap it up by giving you a few hints of how you can quickly use this algorithm for any problems that you are given within your tests, within your exams, or within any sort of assignment. So let's get cracking. So what is Dijkstra's algorithm? Dijkstra's algorithm is basically used to find the shortest path between nodes. So in other terms, what we are saying is we want to find the shortest path mainly from the fixed or the start node to every other node. And this path is the least cost or the smallest cost or the smallest distance path that we want to find. Okay, so that's basically what Dijkstra's algorithm is about. We want to find the shortest path or find the reduced or the least costly path to ensure we create more efficiency and reduce the cost. So what is the principle around Dijkstra's algorithm? So this principle basically says if we have the distance of the current node, I'm going to represent that with Cn, plus the length of the current node Cn and the target node Tn, it will always be less than the distance of Tn, which is the target node. So that in turn means that the distance of the target node Tn is equal to the distance of the current node plus the length between the current node and the target node. Okay, so if the distance of the current node and the length between the current node and the target node is less than the distance of the target node, then the distance of the target node is equal to the distance of the current node plus the length between the current node and the target node. That's basically the principle. If you're a bit confused at this time, don't worry about it. You'll actually see this come together while we are doing a few examples. Let's tie this to a real world application. So in the real world, an example that we might have is cities. What we have various cities. We can basically use Dijkstra's algorithm to calculate the shortest path or the shortest route. So the shortest route between different cities, because you might have more than one way to get from one city to the other, but you'll want to always ensure that you want to get to the city in the shortest amount of time, which is usually the shortest distance that you want to use. So if you have multiple roads going from city A to city B, you always want to find the shortest road that will get you from A to B in the shortest amount of time as well. Another example you can maybe go and look at is maybe Google Maps. Go look at Google Maps and check if they do the same thing, because when you do use Google Maps, they can give you various routes as well as show you the different times that each route would take. And of course, they give you the option to choose which route you would like to take, but the first option is always the shortest route. So have a look at Google Maps, do some research around that, and see if they are also using Dijkstra's algorithm. Let's look at a quick and a simple example, right, of something like this. Let's say we have 3 points or 3 nodes. We have A, we have B, and we have C. Okay, so we have A, B, and C, and we have this as 15, we have this as 15, and we have this as 50. Okay, we can find the shortest path from A to the other nodes by using the principle, or just by looking at this, and we can see that the distance, basically the distance, let's use another color, the distance between A to B is equal to 0, because A, distance between from A to itself, is 0 plus 15 that we have up here. So we know that this is 15. So from A to B, it's 15. Then we can take the straight line distance from A to C, and we can see if we go from A to C, that is also 0 plus 50, which is equal to 50. Okay, so distance A, straight line distance here, A to C, is directly 50. But what if we want to take another route to get to point C? So what if try to get to C from A via B up here? So if we want to do that, we would go from A to B to C basically. And we already know the distance between A to B, as we calculated it already, is 15. And if we can see from here, the distance from A to C is also 15. And that is 30. So we can see that going from A to B, then to C, is actually shorter than going directly from A to C. Okay, so that's basically what Dijkstra's algorithm is trying to show us, which is the shortest path between your start node or your current or reference node, and how you can get to each of the other nodes using this specific algorithm. And this example clearly explains it to you, right? We could have went via the straight line here, if we needed to go to C. However, it was costing us more, or the distance was quite more, which was 50. But if we went from A, B to C, it was shorter. So think of it like the example of cities. If we had city A, we had city B, and we had city C, and you wanted to get to city C, if you went straight from city A to C, you would have traveled a longer distance, which meant a longer period of time, compared to you going from city A to city B first, and then from city B to city C. Okay, so quite a simple example right here. So next up, what I'm going to show you is a few steps of how you can implement Dijkstra's algorithm. Don't be afraid of it. You would practice will make perfect, because a lot of the steps that you perform during this algorithm is repetitive steps. So stay tuned. I'll take you through the steps next, and then we'll get into some examples. I'll start with an easy example and then take you to a more difficult kind of example, also showing you some hints, as well as maybe an obstacle here too that you might need to think and decide what you need to do. So stay tuned, and we will go through the steps up next. Okay, so let's look at the steps, right? I'm going to give you the steps, and then we'll jump straight into an example, because you can learn better just by looking at the example. But however, these are the steps, right? Step number 1 is we must always make sure that we are keeping track of all of the visited nodes and the unvisited nodes. Okay, so basically you can create an array and call it visited, and create an array of all the nodes A, B, C, and the unvisited array you can create as well, just to keep track that you haven't visited D, E, and F. Okay, very important to keep track of this, because we should only be visiting a node once and not more than once with this algorithm. So keep track of all the visited and unvisited nodes. Then, when we first start off solving the problem or the question using Dijkstra's algorithm, we need to first assign the start node with the distance of 0 and all other nodes with the distance of infinity. Very simple reason of this: if your start node is A, the distance between A and A is 0. However, when we are starting to work through using Dijkstra's algorithm to work through the problem, we at the start do not know what is the distance between point A and the other nodes. So we're going to make it the highest value, which is infinity. So basically, what we are saying is we have points A and B. When we first start, we know the distance between A and A is 0. We're going to write it down as 0, and we're going to leave B as infinity because we don't know at this point what is the shortest distance between A and B. Okay, so that's basically what we are saying. Also look at this table. I suggest you copy down the columns in this table because we will be using this type of table to solve the problems. In the first column, we'll look at the node that we are focusing on. In the second column, we have the shortest distance from the start, and in brackets I put A. Now the reason for me putting in A is in this case our start is A. However, you could get a question where the examiner will already tell you what is your start. So in some cases, your start could be E, could be F, could be G, any other point. This is just to remind you which is your start, right? So you don't get confused. And then, as was mentioned earlier, we need to keep track of what was our previous node. Okay, so that's step 2. Step 2 is very important. Now comes the repetitive steps, right? So step 3, we need to visit the node with the smallest known distance from the start node. So if we have node A, which is our start node, we have node B and node C as well. And the distance between A and B is 2, and the distance between A and C is 1. This is basically saying that the next node should be C because the distance is smaller. Okay, we will see this a lot. This table here will actually help us, especially the distance table will actually tell us which will be the next node, right? So when we look at the example, you'll actually be able to pick that up. Then step 4 says that we need to examine the current nodes and the unvisited neighbors, right? Remember, we can only visit a neighbor once. We can't visit more than once. That's the reason for us having step 1, where we have the visited nodes and the unvisited nodes. Then with reference to the current node, we must ensure that we are able to calculate the distance of each neighbor from the start node. Okay, and you saw earlier on where I had simple example of ABC. That's what we basically did, where we are able to calculate the distance of each neighbor from the start node A, and we saw that going through city B was faster than going directly from A to C. Okay. Then next step, if the new distance of the start node is less than, very important, right? If it is less than the known distance, update the shortest distance in the table. So this is basically saying that if we found a node earlier on that the distance was 5, and then we did another calculation with a new node, and the new distance is 3 for that node, then we would take this new distance and replace it. Okay, so that's basically what it's saying. We want to find the shortest path, so we always want to get the smallest distance between each node. Step 7, update the previous node for each of the updated distance, exactly what I just explained. And then we must always keep track of the visited nodes, right? Keep track of the visited nodes. We don't want to revisit that node, and by keeping track of the visited nodes, we will then be able to find the shortest path, right? Because the shortest path will not always be ABC in order. Okay, and then of course we just need to continuously repeat steps 3 to 8 until all the nodes are visited, right? Ensure that all the nodes are visited before you complete or stop performing Dijkstra's algorithm. Okay, so that's basically the steps. It might look quite long, 8 steps in here, but once you start working through some of the examples, it will come naturally to you. So just to recap, right, the steps. we need to ensure that we keep track of all the visited and unvisited nodes, keep an array of the visited and unvisited nodes. When you first start up the problem, ensure that your start node has a distance of 0 and all of the other nodes are of infinity. Then we need to ensure that we visit the node with the smallest distance from the start node next. So we always do that, and by using the table as shown above here, in the second column, you'll definitely be able to pick that up. Okay, so just ensure that you are able to pick that up. Then we need to examine the current nodes against the unvisited neighbors. We then, with reference or respect to the current node, we need to calculate the distance of each neighbor from the start node. Then ensure that the distance of the node, if the distance of the node is less than the known distance that we currently have in the table, ensure that we update the table with the new and the latest shortest distance. If it is more, then we can ignore. Okay, and you'll see that in the examples. Then we update the previous node for each of the updated distances, and then we just ensure that we keep track of the visited nodes because that will give us our shortest path. Okay, and then of course repeat these steps. So those are the quick steps for you to just understand of how we're going to do it, but we're going to jump into an example next, and you will actually see how these steps will naturally occur while we are doing that example. So stay tuned. Let's jump into that example straight away. Okay, so let's look at this example, right? So we have the nodes or the cities A, B, C, D, and E. Between A and B, we have 6. Between A and D, we have 1. Between B and D, it's 2. Between D and E is 1. B and E is 2. B and C is 5. And E and C is also 5. Okay, so please pause the video here, draw this diagram, take it down because this is what we're going to work with, and also prepare the table on the right. As you've seen in as we've been going around along, this is the table that we will be using with the node in the first column, shortest distance in the middle column, and the previous node in the third column. And then also don't forget to have your visited nodes in your array as well as your unvisited nodes. And as you can see right now, we have not visited any nodes, so we will populate the unvisited nodes as A, B, C, D, and E. So we have all of them which are unvisited right now. So that will take care of step 1 that we have for this problem, or for this Dijkstra's algorithm that we're going to use, and we're going to move on to step 2, right? Step 2 states that we are using A as our reference or start point, so the distance would be 0. For B it will be infinity, for C infinity, for D infinity, and for E it will be infinity. Okay, so that takes care of step 1 and step 2, and now we're going to move into using the repetitive steps next, right? So since A is our start point, we're going to look at the 2 neighboring nodes, and as you can see, the 2 neighboring nodes here is B and D. And looking at the distance between A and B, we know that the current distance for A is 0, so it's 0 plus 6, which will give you 6. So we're going to change B to distance being 6, and the previous node here would be A. Then looking at D itself, we know that the current distance for A is 0, and then we need to add the 1 in here. So 0 plus 1 is 1. So D here, we're going to have this as 1, and our previous node is A. Okay, so that's basically this part of the step, but we're not done as yet. We need to ensure that we populate the visited nodes. So we know we visited A right now, and we can remove A from here. Okay, so we're keeping track of the visited nodes so we don't visit those nodes again. I also like to actually do a tick on here, just like a pencil tick, just to ensure that it's also visible to myself on the table as well. So the next part of the algorithm states that, or the step is, are now going to look at the next shortest path. So the next shortest path, or the next shortest distance, is D. Okay, from here you can clearly see that D is the smallest, it has 1. So we're going to look at D, which is here. The neighbors to D is B and E. We are already done with A. We don't go back to A. Okay. So looking at B with respect to B and E, we already know that the distance from the start point for D is 1. So we're going to have 1 plus 2. Okay. 1 plus 2, which is up here by B, that is 3. Currently, we see that when the previous node was A for B, the shortest distance was 6. So because it's now 3, which is smaller than the shortest distance, we are going to change this because that's what we want to find, the shortest distance. So this is 3. And now our previous node changes from A to D. Okay. Then between D and E, right? We know that D is already 1. So 1 plus 1 is going to be 2, the one we're getting from here. The other one we're getting from what we already found when the previous node was A for D. So that's now going to be 2 for E, which is already infinity. So 2 is of course smaller. So that's going to be 2. And our previous node here is going to be D. So we are basically done with D because we're done with the nodes. So we now need to update our array. So we now visited D and we can get rid of D from there. Okay. So what do we do next, right? We need to look at which is now the shortest path, or the shortest node right now that we have not visited. And like I said earlier, I like to tick off the ones that we visited on the table itself, so it's also visible to me. So I'm going to tick off D. Okay, so what do you think is the next shortest node that we need to look at? If you can look here at the table right now, we can see it's E. Okay, we can't use D because we're done with D. So if we're looking at E, E has 2 neighbors as well, which is B and C. So let's look at B first. E is already 2. Okay, and the distance between E and B, or B and E, is 2. That takes it up to 4. 4 is bigger than 3 right now. That's in the table for B. So we are not going to make any changes here. We would ignore it, right? Main aim, shortest path. 4 is going to make it the longer path. So let's look at C then. The distance between E and C here is 5. So 5 plus 2 is 7. So C currently is infinity. So we are going to get rid of that infinity and we are going to replace that with 7. And the previous is E. So we're going to change this and we're going to add E to this list. Okay, and then we get rid of that from the unvisited list. Okay, so we are now done with E as well. Cool. So just ticking, as you can see, you can visually see which are the unvisited nodes as well on the table. So just having that pencil ticking there helps as well visually. So now we're going to look at the next shortest or smallest distance, which is going to be B because it's 3, so smaller than the 7. So B has 2 neighbors, which is E and C. We know that we've already visited E, so we can't go back to E with B. So we're going to look at B with respect to C. So the distance between B and C is 5. Okay, and it's already, and B is already 3. with respect to A. So the shortest distance here is now 8 with respect to C. So 8 is greater than 7, so we're not going to make any changes down here. So with B, we're not going to do anything further. We are, however, going to add it to the list to say that we have visited it and remove it from here. Okay. So just note, right? We didn't do anything with B because B's neighbor is E and C. E is already visited. We are only allowed to visit once. And looking at B and C, so it's going to be 5 plus 3, which is 8, and that's bigger than 7, right? So we're not doing anything with B right here. So we're going to tick that off. Finally, we look at C. C has two neighbors, which is B and E. And similarly to B, we are not going to do anything here because we have already visited all of the remaining nodes. So all we need to do is just add C to our visited list. And we are now done with C as well. Okay. So what is the shortest path, right, to get from A to C? It is 7, right? That's what we have right here. Just want to change the color, but let's see something bright. So it is 7. Okay, but what is that path? For us to find or figure out that path, the previous node column comes into effect right here. So we can start with C because when you get from A to C or vice versa, C to A. So we start with C. We know from C the previous node was E. So we went, let's use a different color. I'm gonna call it out. Let's make it a bit bright. So we went here, okay, and that was the 5 that we have. Then with regards to E, if you look at E, which is down here, E, the previous node for E was D. So we went in this direction, okay, and then if you look at D, which is down here, the previous node was A. So we went up there. So that's our shortest path from A to get to C. So it's A, D, E, C. And if you look at summing the distance, it's 5, 1, and 1, which is 7. And that's the 7 we have here. Cool. So that is the first example. Quite simple. Take notes of all of the hints that I gave you through it, especially when using the rules. Also ensure that you do not waste time. The main rule or the main reason we have the visited nodes array is to ensure we don't revisit these nodes, because you would waste time or get the incorrect answer like we had with B here as well as C. We didn't need to go back and visit E. E was already done. And with C, we didn't need to go to B or E because both were already done. Okay, so stay tuned. I'm going to go into another example next, a bit of a longer one, but as well going to give you quite a lot of practice. So also get ready, draw up the table, get the table ready. I'll show you the diagram or the graph diagram next, and then we can take it from there and look at how we solve that diagram using Dijkstra's algorithm. Okay, so we're going to look at this example. It's going to be the final example for the video. So just pause the video here, take down this diagram or this graph for you to use. So we have A, B, C, D, E, and F, where we have the weighting of 2 between A and B, 8 between A and D, 5 between B and D, 6 between B and E, 3 between E and D or D and E, 2 between D and F, 1 between E and F, 9 between E and C, and 3 between F and C. Okay. Don't forget to have your table on the right with the node, the shortest distance, as well as your previous node, and then have your array of unvisited nodes as well as your visited node. Okay. So we're going to start with the first step. Okay. First step is, because we have set A as our start point, so shortest distance for A is 0. The rest is all infinity, infinity, and infinity. Okay, so everything else is infinity. Now, we are then going to look at which at A with B as well as D, because those are the two neighboring, or the two neighbors to A. Okay, so looking at B and A, we know that's going to be 2. 0 plus 2 is 2, so we're going to make this 2, and we're going to make this A. Okay, with respect to D, so A to D, D is here, so we're going to make that 8, and your previous node is A, and we're now going to say our visited node is A. Okay, the start is very easy. Everything previous is 0, so whatever's on your lines here would definitely be what's your shortest distance first as you're going along with it when you start with A. Okay, so we have the visited node is A. You can remove A from here. So rewrite this quickly. So this is B here. Okay, so let's move on to what are we going to identify next. This actually still looks like infinity. Let's get rid of that. Make this more of a straight 8. Okay, so what are we going to do next, right? So the next thing we know that we need to do is look at which is the next smallest or shortest path that we must look at. So looking at our table, so table comes very in handy here. We know that the next one is going to be 2, but before that, I'm just going to mark A on here as well, right? So we're going to look at B, right? So taking B, we know B, the two neighbors are E as well as D. So if we take B, okay, with respect to E, we're going to get 8, okay? Because 6 plus 2 is 8 for B with respect to E. Okay, so we are going to make that change right now. So we're going to get rid of the E here, and we're going to make this 8, and that is now B. And we also have B with D. So B with D is going to be the 5 from here plus the 2, which is the 7. However, previously we had A and D as 8, so 7 is less than 8, so we're going to get rid of the 8. We're going to make this 7, and we're going to change our shortest path, or the previous, from A to B. Okay, so that was another good case where we could actually clearly see that the shortest path, the new shortest path, or the new distance was shorter than the previous distance, so we needed to make that update. So heading along, let's update here. So we went A, we went to B, we can get rid of B from there, and we can tick off B from here. We have now visited and used B. Okay, so we now have A, B. We still have C, D, E, and F to go through. So let's look at the next shortest path to go ahead with. We can't use B. B is 2, but we can't use it. We already used B. So we would now need to use 7, which is with D. Okay, so now D is our next, or our current node that we're going to use, and D is now connected to both E as well as F. So let's use D with respect to E first. So we already know that D is 7, and if we are going to add another 3, so that's going to take us to 10. So we're going to leave the E as is. We're not going to change E right now. It is at its lowest or its shortest distance right now. But what about D with respect to E? We can see that D is 7 currently, plus 2 here for F. That's going to take us to 9. So we can now change the infinity here to 9. And that is with D as our previous node. Okay, so we are basically done with D. We add D in here. We can now get rid of D from there. Okay, I'm just gonna add C back with this call. So D is now done. We can now move on to the next step, right? Don't forget, I like to tick this off, so I'm also done with D on this table. I'm now gonna look at what is the next smallest or shortest distance that we can use. Now we can see that the next one is 8, and that belongs to E. So we're looking at E up here. E goes and has the neighbors of F and C. So looking at E with respect to F first, we know that E is 8 plus 1 here, which is 9. So both are the same. What do you think we do in this case, right? We can leave it as is. So if it's same, so the hint here is if it's the same, just leave it as is, because we're trying to find the shortest path, right? So we're going to leave it as is, with still at 9 and the previous node being D. What about E with respect to C? Okay, so the C here is 9 plus 8 here. So what does that give you? 17, right? So 9 and 8 here is 17. So we can already see that we can change the infinity here for C to 17. Okay, so that's 17, and we're going to change the previous node to E. Okay, and then we can add E to our visited list and get rid of E down here. So now we just have C and F remaining. Okay, and then like usual, I'm going to get rid of the E that we just used. So that's gone as well. Now, what is the next node that we can use here? So the next node, or the next shortest node we can use here, is F. Okay, so using F, we know that F is connected to E and C. However, we've already visited E, so there's no use going and calculating for E. As per the algorithm, we're just going to calculate for C. So we know F is 9 plus the distance between F and C, which is 3, and that takes us to 12. Okay, so we can now, 12 is less than 17 for C, so we can change the 17 here to 12, and we can get rid of the E here. We are now going to make this F. Okay, so we are now done with F. We would also take this off. F is now done. We only left with C. However, all the nodes that C is connected to, which is E and F, we've already visited, so we don't need to do that. We can add C directly into our list, and we get rid of C down here. Okay, so this is it. We are basically done. Okay, so if we were looking at this, let's do the same step we did previously. I just want to show you how this looks. Let's use this color. Let's use a better color. Let's use this, right? So if you're getting from A to C, we're going to do the same thing we did previously. We're going to go with C here. So C here the previous node was F, so we went in this direction, which was 3. Then for F, the previous node was D, so we went here. Okay, Then for D, the previous node was B, which was up there. For B, the previous node was A. So we went with 2, 5, that's 7, 2 again, okay? Then we went with the 3 here that took us all the way to 12. Okay, so 5, 2, 2, and 3. Okay, so that's how we found the shortest path here from A to C. So A, B, D, F, C is your shortest path to go from A to C itself. Okay guys, so that takes us to the end of this specific video in Dijkstra's algorithm. If you do want more examples, please look at the description. You can email me, chat to me on Twitter as well. So have a look at these two examples. They're quite good examples. They try to show you as much of Dijkstra's algorithm being used as possible, as well as some of the hints. And when you are done, always ensure that you go back and look at the previous nodes like I did here. Trace it back and just make sure that your value here is the same as the distances that you have in here, just to make sure and mark your own work to ensure that they are telling up and making sense to what you have in the table, as well as what you have in the existing graph that you were given, to ensure that it is the shortest path. Continue practicing. That's the best way I am known to get Dijkstra's algorithm right and correct. You will get a bit more complicated examples where you'll have a whole lot of other nodes, so try those out as well. But like I said, let me know if you do want any other examples. So thank you for watching, and then until next time, I will be uploading more videos, hopefully more on a weekly basis, to get you up and running, especially with all of your exams that you may be heading into when this video was recorded. But good luck and all the best.